there's a very strong interest in energy efficiency from these high-performance data centers, really driven by data analytics. And it's not just Facebook, many others, as you can see. And as you know, this has been the special theme of this conference, so it's well known. But certainly the deep learning and the data analytics and the machine learning, it takes a tremendous amount of compute power to do that. And so, you know, actually solving these problems, these are just some quotes, in terms of the evolution of the performance of these AI systems, and again, the commercial need and drives for that are just beyond, you know, you cannot really exaggerate the growth of that at this point in time, in my opinion. And so these are really driving these systems, and so to drive them faster in an energy efficient way is of keen interest to a lot of these vendors. And in fact, Facebook and NVIDIA, these are their entry into the top 500, are essentially these very large GPU clusters. Interesting. Okay, so now this is the question that I ask. You know, given all of that, this is the landscape. What can photonics really bring to the table? Let me just remind you. This is kind of where we are approximately today in terms of orders of magnitude. So I like to sum up the photonics story with this slide. This was actually part of an ASCAP study that was led by Bob Lucas a few years ago. It still holds. So the story with photonics is that the optical interconnects, they're essentially driven by electronics to drive the bits, create the bits from the laser. I'll go a little bit into that. You know, all of that takes electronic circuitry, detect the optical bits, and so forth. So they more or less start out at the same energy as the electronic interconnects, right? And you can put that number, you know, however your devices are, however you design your optical devices, electrical driver circuitry. But it's pretty much wherever electronics is, this is how well we can make the optical devices energy-wise, energy per bit-wise. Now the difference happens when you move the data. So you generate the data, detect the data with the same energy efficiency as electronics because it's basically electronics at those endpoints. However, because of the essentially low loss of the optical propagation waveguide, the optical propagation fiber, whatever is the transmission medium, it's extremely low loss, does not require re-amplification, regeneration. That energy can remain more or less flat, independent of distance. Now it's not exactly independent, you have to re-amplify and regenerate sometimes, but it's much more independent of distance than anything else that we have. Whereas with electronics, as we know, as soon as you get off the chip, as soon as you go across the system, the energy starts to escalate and escalate. Because of that energy kind of flatness, I can maintain the same bandwidth density across my system. So imagine that I could have the same bandwidth density, the same amount of communication bandwidth that I have as today on the chip, but have it really across the entire system. So I can communicate across the data center or the system with as much bandwidth, those terabytes per second that I showed you, as I have on the chip, as I have locally on the chip. This is the key advantage. This is what it can bring to the table. But how do you actually do it? Photons are somewhat fundamentally different than electrons. So we need to rethink a few things. We want to try to do it, as we say in medicine, right? Minimally invasive. We don't want to get everybody too excited and uncomfortable. So we want to make it look like the system doesn't actually have optics in it, that it's electronics. It's the same as you always had. You don't have to change your software. But you still need to do something specific because the optics doesn't switch the same way as the electronics. There's no optical buffers, there's no optical packet switching per se, kind of a different technology. So how do you do it? The first part is just basic. You know, you want to just squeeze out the most efficient, energy-wise, and bandwidth density-wise that you can from your link. This is the cartoon of the optical link. I'll show you how it works in just a little while. The second thing is, okay, once I have these optical links, these optical wires that are extremely bandwidth dense, I want to connect them into my compute elements. Memory, GPUs, CPUs. How do I do that? What's the packaging? What are the details engineering behind that? I'll show you that. And then once they're connected, they're part of the interconnect fabric. It doesn't mean I'm taking away electronics. I still have electronics there. I still need to use the electronic packets, switches, and so forth. But I do have optical connections to these resources. And then the third part is I take advantage of the